Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you so much for taking part of your day to come out here. We're thrilled to have you. Welcome to Seattle. More specifically, welcome to Redmond and to the Microsoft Corporate Campus. My name is Dirks. I'm the Director for Education and Scholarly Communication on the Microsoft Research Connections team. And a little bit of background about myself. I'm a librarian. Yay! I actually went to 2 library schools. One was not enough. So I got my master's degree at Chapel Hill. Do we have any Tar Heels in here? 1, 2, 3. All right. I'll see you later at the Duke game. Okay. We're gonna be watching some basketball tonight. I got my master's at Chapel Hill, and at the time when Columbia still had a library school, I went up to Columbia and got a degree, postmaster's in preservation administration specifically. And I'll spare you my whole career, but career progression. But I was very lucky enough in 1996 to be named Microsoft's corporate archivist. So I started here about 15 years ago as the corporate archivist. Ended up managing the corporate library for a few years, moved into marketing, if you can believe that, and worked in market research for about 5 years. And then I was lucky enough to run into this guy, Dr. Tony Hay, at I think it was a library fundraiser event at the University of Washington. And he said, what's a librarian doing over in marketing? You need to come over here and research. So I was lucky that he lured me over, and I've been in his team about a little bit over 4 years now. Just to quickly tell you a little bit about the team, Microsoft Research, Dr. Peter Lee is going to give you a more in-depth overview of Microsoft Research. But Tony's team is technically responsible for our external research collaborations. So all of the things that Peter will be talking about, Tony is very interested in across a variety of different theme areas, or kind of a portfolio of looking out and working and engaging with the academic community on specific research projects or research areas that Microsoft is interested in. My specific area, as I mentioned earlier, is education and scholarly communication. And that is where we look at the libraries playing a huge role. Traditionally played a role more at I'd say at the end of the life cycle of collecting these materials, but I think we're doing a fantastic job, but we need to do a better job of working in earlier in the research process and starting to gather data, collect that data, curate that data, etc. So that's a little bit about me. Microsoft Research has been the sponsor of the iConference, I think, 3 out of the last 4 years. It's something we see a lot. We're very interested in this community. We see a vital role for librarians and information professionals in a world of data-intensive science. We're going to be speaking a little bit about that. And this is a community we want to continue to engage with. Over the course of the day, you're going to hear a lot about Microsoft Research. You're going to see and meet some of our researchers and get a little kind of deep view into their research areas we hope that you'll be interested in. It's going to be a pretty broad palette. There's going to be things kind of all over the map, but I think you'll see the applications and the potential. And then in the last session in the afternoon, we have folks that are going to be coming from our product groups, from different specific products or technologies that I think you'll see some interesting cutting-edge things. So we have folks working with Surfaces, folks working with Connect. You'll see a user experience guy from Connect. I think you'll find it very, very interesting. So logistics, just very quickly, I think everyone's got a lunch. Drinks, you'll saw that there was water in the back, and again, there's soft drinks down the hall, coffee, tea, and still water if you want that as well. So feel free. The other thing I was going to say, we're going to point the fire hose at you for the next 4 hours. So if you need a bio break, feel free to duck out, or if you want to get a drink, we're just going to keep talking, and we're going to ask you guys. We are going to take one break from about 1:15 or 1:20 until 1:30. Hopefully by now you've seen the wireless codes, and you know that there's power in the floor if you need to plug in your laptop. And I think I might have covered all of the logistical points. So with that done, I welcome you again. I was very, very excited to have all of you here, and I'd like to invite Peter Lee to come up and tell us about Microsoft Research.
Great. Thanks, Lee. It's really great to be here and to welcome you to Microsoft and Microsoft Research. My name is Peter Lee, and I think I can recognize a couple of familiar faces. You probably, if you do know about me, I was, last time you saw me, a computer science professor and the department head at Carnegie Mellon. And then I had a short stint at DARPA. But for the past 3.5 months, I've fallen over to the dark side, and I'm now the managing director of the lab here in Redmond. What I've been asked to do is to give you a little bit of an introduction to Microsoft Research and what we do and what we're about, and so let me just do that. We are, just in a nutshell, a lab dedicated to expanding the frontiers of possibilities in computing and expanding the modes of human experience as they relate to computing. And that is something that's very important for advancing the field. It's also important for the future of this company that is completely committed to computing and computing technologies. We have a mission statement, and this mission statement has been the same for 19 years. We are 19 years old, in fact going on 20 years, and for the entire history of Microsoft Research, this mission statement has been the same. And it's worth going through. It's remarkable in its simplicity. First, we have the mission to advance the field in the areas we do research. That statement is actually a bit subtle. Advancing the field means that we're committed to doing basic research, even in the foundations. And as I'll get to in a little bit, you'll see that we do really a broad range of different kinds of research activities, some very, very much blue sky, others really directed at helping our product teams. The other is in areas we do research. And what that implies is a level of autonomy and independence. No one in the company is allowed to tell us what to work on or on what problems we choose to tackle. Microsoft Research, within the context of Microsoft, is an autonomous, independent lab that sets its own agenda and pursues research in the manner that it chooses. The second part of the mission is to transfer research results as aggressively as we can into products. And as I'll also explain a little bit later, you'll see that this is a constant concern of ours. How can we bring more and more great technology and research advances into the things that Microsoft sells? And then finally, ensure that this company has a future and more broadly that the computing field has a future. And so some of the things you'll hear from Tony Hay and External Research really pertain very directly to ensuring that the computing field very broadly has a future, and we engage in this as well. And that's important to us because the more that we expand the possibilities for computing, the more that Microsoft has opportunities. So this mission statement has really been a remarkably simple and direct and consistent part of the 19-year history of MSR. Now, I'm managing director, and I have a little bit of a joke. You know, at Carnegie Mellon, I was a department head, and so as you know, if you're at a university, I had no authority there and lots of cats to herd. I then went to DARPA, and I found it stunning. I had absolute military authority, but there were no cats. Now here at Microsoft, I have a tremendous amount of authority in the corporate hierarchy and lots of cats, but I'm not allowed to do any herding. And why is that? Well, we have a culture here in Microsoft Research that, roughly speaking, goes like this. What's my job? Hire the best people, make sure they are fully resourced, and then get out of the way. And in reality, I have a prime directive from my boss not ever to tell researchers what to do. And so it, as much as possible, is a bottom-up organization. Now, Microsoft Research is a pretty big and complicated place. We have 8 locations around the world, and so the sun never sets on Microsoft Research. There are 3 big labs. The big one, the mothership, is here in Redmond, which is my responsibility. The 2 other big labs are in Beijing and in Cambridge, England. Then there are 3 smaller labs in the Silicon Valley, in the Boston area, and in Bangalore, India. And then there are 2 much smaller research centers, one in Aachen, Germany, and the other in Cairo, Egypt. All of these labs really work together, and in total we end up having about 900 PhD researchers and research engineers. Here in Redmond, we have about 350 of those 900, 260 of them being researchers, PhD level researchers, and about 90 being research engineers. So from the perspective of a university-like structure, you can think of Microsoft Research Redmond as like a school or college at university. And in fact, we're organized into 10 departments here in Redmond. Now, what do we do here in Microsoft Research? And to explain that, I use a kind of a rubric that I also used at DARPA, which is a quad chart that maps out the space of basic research investments and activities. On the x-axis here, we have research activities that span short-term managed risk research activities to longer-term activities, research activities that require some patience in order to bear fruit, sometimes a very long time, a decade or more. And then on the y-axis, we have a span of research problems spanning reactive types of problems, pain points for product groups, or societal problems that we understand today and know that we want to solve, all the way up to the more open-ended search for truth and beauty, the search for disruptions. And the thing that's important to understand about Microsoft Research is that we try to cover this whole space. And if we map out the quadrants of this, we have in our organizational structure here a demand that the lab actually create significant impact across all of these quadrants. And these 3 blue quadrants in particular are things that I refer to as the lanes of basic research. Let me describe a little bit about what these are. On this lower left quadrant, we have short-term reactions to ongoing problems. So for example, and I refer to this as mission-focused activities. So for example, you might have heard that we're engaged in a holy war of sorts in search. And that is a technical problem that can be broken down into ideas and approaches that really hit on the leading edge of the state of knowledge in machine learning, in large-scale distributed systems, in economic models. And so, for example, on the specific problem of the quality of the relevance of search results, which is a measurable activity, we know that we want to beat Google. And by the way, let me brag that we are beating Google. And furthermore, that's the kind of activity that really requires bringing absolutely state-of-the-art concepts in computer science to bear. And so we have mission-focused activities that react to those kinds of known problems and try to make progress. On the upper right corner, we have pure blue sky curiosity-driven research. And we have a substantial amount of activity that is like that. Some of it is purely theoretical. Some of it is applied, but blue sky in the sense that the company doesn't necessarily have an obvious interest in the outcomes. To give you an example of that, let me just brag a little bit. Yuval Perez in our theory group in this lab just won the David Robbins Prize, which is a very prestigious prize in algebra, for being part of a team that computed the perfect arrangement of wooden blocks to get maximum overhang over the edge of a table. And furthermore, proved the lower bound on how far you can go given a number of blocks. And there you can see, I think that's a 30-block arrangement. And you can see you have to make a very judicious use of counterbalance kind of arrangements. And yes, we do try these in reality. In the orange behind was the previous known best solutions. But now we know actually how to optimize this. Why does Microsoft care about this? Well, today Microsoft probably does not care about this. But the point here is that sometimes, in fact, more often than you would think, somewhere down the line it becomes important for Microsoft to know how to solve these kinds of problems. In the applied space, we were very deeply involved in cognitive radio and in solving key technical problems in using the dynamically available spectrum for much, much more extended Wi-Fi access. The fact that we didn't have an obvious business interest in this made it possible for us to influence the FCC chairman to change government policy to allow white space of spectrum to be used. And so we engage in quite a bit of that kind of blue sky activity. On the upper left quadrant, we have a very, very interesting set of activities where looking at our understanding of the world today, so that's a short-term focus, how we understand the world today, in what ways can we be completely disruptive. And so, for example, when we think about how people should interact with computing, we think very hard about a domain that we here refer to as natural user interaction, or NUI. And that kind of thinking can be very disruptive in the short term. So, for example, in a very short amount of time, we were able to engage with the Xbox product team in order to develop the technology around Connect. And so both the 3D image processing as well as the steerable microphone array technologies are ideas that at one point, 15 years ago in this lab, were blue sky, but a decade and a half passes and suddenly there's an opportunity, based on our understanding of the world today, to be completely disruptive. And then in the lower right, while I've graded out, and I've graded out because it's an area that has somewhat less investment, but is also important for the company. And these are areas where there's a less time-critical but still important process of continuous improvement or sustaining of capabilities. So some of you might know that we ship a very large number of language translation technologies in our various products, like Office. And every day we have to make them a little bit better. Just 2 weeks ago I received a report that our English to Russian translation BLU scores were not up to the same level as some of our other language translation products. That's a kind of a problem that requires a room full of PhD researchers to fix. You can't just expect a product group to do that. On the other hand, it's not going to be the end of Microsoft's business if we don't fix it tomorrow. It's something that we just work on every single day in order to make improvements. And internally, we do a huge amount for developer tools. The world outside sees the technologies in things like Visual Studio. Internally, the amount that we do in order to support developers and help them have predictive power on where problems are going to be is enormous. And these are things we work on every day to continuously improve what we do. So in Microsoft Research, these lanes of basic research are all equally valued, and we really push hard on all of them. As a lab director, my demand of the lab and of my direct reports is to show significant impact in all of these quadrants. Microsoft Research Redmond overall is a very interesting place. It's a big place. So just Redmond is 350 computer scientists and engineers divided across 7 research departments, 2 mission-focused research centers, and a pretty substantial engineering team. And at least from my experience, this is a real challenge to try to even just to understand everything that's going on. On the other hand, within Microsoft, we're tiny. The whole of Microsoft Research is just 1% of the company. Of course, we are highly visible within the company. And so you would, just given our visibility, particularly with the senior leadership of the company, you would expect that we were 20% of Microsoft. But we're not. We're just 1%. But we're very, very high impact 1%. And it's a very interesting thing that we are just so different. So you could view Microsoft as being a very execution-driven company, and then it's carved off just this little tiny bit to try to think differently. And we're impactful. It is literally the case that every single product and service that Microsoft offers has had key contributions by Microsoft Research. So as small as we are, the impact is enormous. So what I'd like to do now is do something that's a little silly. And some of you might have seen this if you've seen me speak before. And if you have, don't ruin it for everyone else. But one question that I often get from outsiders and visitors, but also even from the CEO and division presidents, is why do we have research? You know, what's the value of research within a company like Microsoft? And that's a really hard thing to explain. By the way, I even get that question from our researchers. And so it's something that is so hard to understand that even if you realize at one point, it's easy to forget. And so I've developed several ways to explain this, and the cutest way is through this test. So what I'm going to do here is show you a picture, and the picture will have a bunch of different colored dots. And so I will give you 5 seconds to count the red dots. Okay, ready? Here we go. 5, 4, 3, 2, 1. All right, so how many blue dots were there? All right, what's the point? We, here at Microsoft, it's stunning how disciplined and execution-oriented this company is. 99% of this company is exceptionally disciplined and focused on understanding consumer needs, doing the product development, lining up the marketing and sales, and making sure that all of that ships on time. And the level of discipline and focus in this company is truly, truly amazing. And that's analogous to counting the red dots. That's what this company does. Microsoft Research is the tiny 1% of this company, though, that wonders about the rest. How many blue dots are there? What are all the different colors? Why are there dots? Are there other things going on? And even though none of that is directly relevant to counting the red dots, what you don't know is down the line whether conditions change, where suddenly it becomes important to know how many blue dots there are. So 12 years ago, when this lab started to engage in computer vision research, there was absolutely no reason for Microsoft to be interested in computer vision. But 12 years later, it suddenly becomes the biggest selling product, hardware product that this company has ever produced. And it's that sort of idea that we produce. We look at the outside, try to understand where the field is going, and try to expand the possibilities. So within Microsoft, we are that special 1% of the company that takes a more questioning culture and flows ideas from the bottom up, not from executives and managers on down. We fail a lot. I mean, most of the things we do don't pan out. And that's oftentimes frustrating for researchers. They invent what they think is the next great thing, and they usually are great things. But for various reasons, especially in the marketplace, the world might not be ready for it. And that kind of failure happens over and over again, but that's what we're able to do. And luckily, in a research environment, you can fail and not get fired, which is not true for product groups. And we push all of the lanes of research. So with that, let me just say this is what we do. And welcome again to Microsoft Research. I'm super excited to be here. I'm still in my honeymoon period. Very excited to see all of you here. And happy to hear from any of you about your thoughts. If you want, you can contact me through that email address. I show that because I'm the 8th Peter Lee at Microsoft right now, so it's actually hard to find me. So thank you very much.
Thank you, Peter.
Yeah.
Are there any questions? We can take one or two questions.
Yes?
Are the blocks frictionless?
The blocks?
Come on.
So there's if you look at the math, the paper is actually quite beautiful. So there's a parameter. So for a coefficient of friction, yes. It's a very, very nice paper. Yeah.
Any other questions for Dr. Lee? Yes.
Yes.
Would you be willing to talk a little bit more about the concept of disruption?
Yes. So disruption is something that I think is extremely challenging for any research organization, including if you're from a university, including your departments. There are two comfort zones. One comfort zone is the zone where there are large communities of researchers that are publishing and really, focused on those certain kinds of areas. We have that comfort zone. We publish openly almost everything that we do. Another comfort zone is if there are societal, or in our case, company needs that are well known. Disruption is an uncomfortable place to be because generally speaking, it means striking out in new directions that don't really connect, in our case, with product groups and don't really connect with where the academic community is going. And so how you encourage and push those things is really a challenge. There are a few things that I found are extremely important there. One is concepts that impinge on the idea of democratization, of mobilizing very large numbers of people or putting technologies in the hands of very large numbers of people to enable surprising outcomes. That's one key strategy. A second is to constantly ask, what is your vision for the application of a research result? Now, oftentimes as researchers, we're susceptible to thinking about the technical problems and then dismissing what we think we want to do with it as just the application. But the vision for the application can sometimes be more impactful and inspirational in a disruptive sense than the research itself. Let me pick a non-Microsoft example of this. Some of you have heard the news about IBM Research getting the green light to go on TV with their Jeopardy playing robot called Watson. If you look at the foundational research there, it's completely core computer science research and information retrieval. And there are many applications. In fact, there are direct applications of that type of research, say, to the Bing search engine. But the vision to say, we're now going to go take this to play Jeopardy is a disruptive concept because it gives you a better chance to stumble across some surprising result or idea. So another thing that we do here is to try to look at the projects that we have and ask again, have you thought enough about what are the possible applications of what you do? And try not to fall in the trap of just worrying about what the product groups would bless, but really try to be expansive. Yes?
Just to follow up on that, the obvious alternative to reactive is proactive.
Yes.
But instead of using proactive, you're using disruptive.
Disruptive. So, my belief is that, so I made a joke here. One of the things I have in my first month here, and I'll bet many of you at university departments have felt the same way because I think I encountered this at Carnegie Mellon also, but it's just really vivid here. At the end of the first month, I offered to give up any performance bonus at the end of the year in exchange for a nickel every time someone told me a story about some great thing that they invented that later became a multi-billion-dollar industry that Microsoft didn't act on. So there's a search engine, there's, the precursors to MySpace and Facebook, slates and so on. And so there is no problem, at least for this lab, and I think for academics, to be proactive. That's what we do. We dream about the future, and we think about that future increasingly in very practical terms. So I don't view that as a problem. That just comes naturally to us. Disruptive is harder, because disruptive is really trying to imagine changing worldviews or shifting paradigms, to use a buzz phrase. And that's much, much harder. And so on the being proactive, we do have a challenge in trying to get people to listen and have the imagination that, yes, this could be a big business for us. But that's something that we're just wired to do, and we do that every single day. The disruptive thing is I think where the truly important things can take place. Yep.
Maybe one last question, but we need to stay on schedule.
Very quickly, one perhaps a little question. The first question is there a percentage of projects that you have in any category? And the second question is, it's known that large corporations are not particularly creative, but they tend to become kind of elephants. So the question is, are there any particular process within Microsoft to get your juices flowing and to get you guys, come up with creative ideas?
So let's see. So this is a great couple of questions. And it's one of these questions that's impossible to answer without sounding a little bit defensive. So let me just say that and very defensively say we've got plenty of creativity. But I think there's in a lab like Microsoft Research, we do a lot of things that are disruptive, and disruptive can have a dark side. Disruptive can mean inventing things that really could emerge as viable threats to the health of this company. And so it is true that there is a very delicate and complicated and constantly changing interaction that we have with the company. So, for example, if we invent, say, new browser technologies, which happens, there are very, very interesting discussions that take place with the Internet Explorer team, just to take that as one example that might be relevant here. And so, and my observation is that no two discussions are the same. The business conditions and the challenges for each of our product groups is different. But it is important that those discussions take place. And so one thing that is important here at Microsoft is that every product group listens to Microsoft Research. Even though we're so tiny, we're engaged with literally every single part of this company. Next month, Tony and I will be involved in a show called TechFest. TechFest will be a big conference where we will show off demonstrations of some of our most exciting research, and 5,000 to 7,000 Microsoft developers will flock to come and see what's going on. I mean, it's just one sign of the kind of set of interactions that we have. But then how we take that to reality is always just a one-off kind of thing.
Just a comment. Yeah. I mean, I think research organizations need to renew themselves, as you say, to continually be relevant. And I think what Rick Rashid has done is trying to make us a little less comfortable, and he's deliberately done that by introducing a disruptive influence. So I think Peter's really great news.
Yeah, so there are product groups that just love us, and then some of the same people in the same product groups also just hate that we're making their lives harder. And that's exactly what we're supposed to do. Yeah.
All right, well, please
thank you very much.
Yep. Dr. Lee.
Thanks, Peter, that was great. That really was good.
And now I'd like to introduce Dr. Tony Hay, who is the Corporate Vice President for the Microsoft Research Connections Group.
Thanks very much, Lee. Thank you very much, Peter. So what I'm going to do briefly is tell you a little bit about a paradigm change, which is the nature of the fourth paradigm. So let me just explain a little bit about what it is. We've been looking, my Research Connections team engages not only with the computer science community, the library community and the iSchools, but also with scientists. And in science, we're seeing a veritable change of scale in the amount of data. We're going to generate more data in the next year than we've generated in the whole of human history and all that sort of stuff. It's really true. and scientists are going to be drowning in data, and how they analyze it and how they report it and how they do their science is going to change. So this was Jim Gray, my colleague, who alas is no longer with us. This was the subject of his last talk to the National Science Board, and he had this vision of science which is sort of relevant to the iSchool vision of ex-info. So he saw that many fields like chemistry or biology were developing different fields like computational chemistry, computational biology, but at the same time as emphasizing the computing, there was also a data and information side, bioinformatics, chemical informatics, and so on. And I now see there's astroinformatics and archaeoinformatics. So, and he felt that scientists really are going to have to struggle to deal with all this data, and you have all this sort of stuff coming in, and you want to get questions and answers, but you have to take the data in, you have to manage, could be large amounts of data, like petabytes, but it could also be just an order of magnitude more than you're used to, so going from megabytes to gigabytes, gigabytes to terabytes, and so on. Knowing about schemas, how to organize it, how to reorganize it, how to share it, and how actually to write it up, how to document all these things. So that was what he saw that scientists were now, in many cases, being faced with. So this is a slide from Jim's last talk, as was the last thing. He saw that we've had experimental science for thousands of years, and encapsulating in the traditional ways of doing science since Isaac Newton and Galileo and people like that, we've encapsulated that into laws of physics which we express mathematically, and we can explore that mathematically, and that's theoretical physics and Maxwell's equations, the Navier-Stokes equations, Schrödinger equation, and so on. We can make predictions and do experiments, and that's the way we've done science for hundreds of years. But in the last few decades, since about 1950, we've had computers. And they actually are, as Ken Wilson, who won the Nobel Prize in the 70s for his work in particle physics, called them the third paradigm. Because how can you do investigations of climate change? How can you do investigations of galaxy formation other than doing simulations? And so he was doing a type of simulation which was only possible on the computer. And so he was doing, if you like, computer experiments. And so to do that, you needed scientists with a, yes, you needed to know experiments, you need to know theory, it doesn't replace them, but you needed to know a new set of skills about numerical methods, computational algorithms, computer architectures, and parallel algorithms. So all these sort of skills were different from the previous ones. So he saw that as, Ken Wilson, as a third paradigm. And what Jim was pointing out is now we're seeing in biology, for example, the genome is going to, we're all going to have our genome sequenced if we want in a few years' time for maybe less than $1,000. And that's going to give huge amounts of data, the possibility of personalized medicine and so on. So we have all this data coming from all sorts of new types of sensor network simulations, all sorts of high throughput instruments, and we need a set of tools and technologies. Now, in the UK, I used to run what was called the eScience program. And eScience, if you like, is a set of tools and technologies to support, you know, combining data, managing data, sharing it, and analyzing it, with visualizing it and exploring it. And you'll see some examples of some of the tools we've been looking at applied to data. So my colleagues and I produced this book, which you'll find in your bag. If you've already got a copy and would like not to take one back, please leave your copy at the back, because we're happy to keep them. But what it is a collection of essays looking at biological healthcare sciences, environmental sciences, the infrastructure you need, and it is looking at a scientist with an IT or computer scientist looking where their field would be 5 years from now. So they're visionary accounts, not particularly Microsoft-based, but just looking ahead as to where science is going. But in parallel with this revolution, there is another revolution which is also captured in the book, in a section edited by Lee, which is on scholarly communication. We're in the midst of a revolution in scholarly communication, and I'll come back to that. So you can get this free. It's the only Microsoft thing, I think, as far as I know, published under a Creative Commons license. So you can download it from our website, articles, the whole book if you want, or you can get a version on Kindle, or you can go and get a print-on-demand copy from Amazon. So just to give you a quick couple of examples of data-intensive, I've called it research rather than science because I believe this is not just science. This data explosion will also apply to the social sciences, humanities, and so on. So I'm guilty of calling it e-science, but really it's e-research, if you like. So this is the NSF are funding the Ocean Observatory Initiative, this is the Juan de Fuca plate, and this is where it goes under the North American plate, so it's a highly earthquake-prone zone. I live on Lake Washington here, and I look to the left. On a good day like this, I see Mount Rainier. On the right, if I lean out far enough, I can see Mount Baker, another volcano, and of course there's earthquakes zones through the lake. So it's very reassuring to me that they're actually going to monitor the earthquake plate, so we might get some data. But what this is doing, they're putting fiber optic cable down on the floor here, and they have all sorts of instruments, which could be just temperatures, could be salinity, but it could also be more sophisticated robots, video cameras, all this sort of stuff. And instead of actually being able to observe what goes on down on the ocean floor, just occasionally when you have a ship going across the top, what they now have is data coming in. Not, you go on this ship, you take the data, you bring it back to the lab and spend time with your grad student analyzing it. Here, data is coming in 24 hours a day, 7 days a week, 365 days a year. The field will go from being data poor to being data rich overnight. And we've been investigating with the oceanographers how you deal with that. Do you use the cloud? Do you use workflows? All these sort of things. So that's an example of a science application. And you'll hear later about some tools for visualizing how you combine geological timescales. This is from the Big Bang. This is cosmological timescales. But how you put all that together and how you can look at civilizations, the biology development, the historical development, and so on. So you'll hear a talk about that. So I do believe tools for helping manage and visualize and put together different data sets in other fields than science are important. But I talked about the other revolution, which is perhaps most interesting to this audience, so let me just say a few words about that. So this is based on a slide that I got in 2005 from a talk that Bill Gates gave, all right? And it was this was the slide, and it's very prescient in my view that you have a document, and rather than a static document, you really want it to be interactive data. You want to be able to find the data. You want to be able to have documents that can change if things get updated. It may be collaborative so other people can work on it. And you may want also to have rankings. You have peer review, but you might have some other rankings, like, for example, they have faculty of 1,000 where academics can rank. This was the most interesting paper last month. And you can actually choose your little network of those. So, what Tony thinks is the most interesting is never as good as what Lee thinks. So you can choose your own social network. And that gives you an alternative to peer review. And maybe there are new ways of doing things. And of course, you actually ultimately also want to be able to reproduce the research. And it's a sad fact that most of the papers that you publish now, it's very difficult to get hold of the actual data that the research was based on. And that's going to be a problem if we really want to be able to build and reproduce the research. So this is a vision as to where you could go with this, be able to mash up data, collect them, use all sorts of technologies to view them. And you'll see some of those technologies today. So this is an example. Here is a typical paper. And the way chemists get data off grafts, they make a Xerox copy, and they take a ruler, and they measure it. And that's ridiculous, because you should be able to click on it and go to the actual data. And you also should be able to click and go to where the curve. You may want to plot something different. You may want to try a different fit. So there are all sorts of richnesses that you can add to make publications live documents. So Jim Gray, in his talk, in this book, we wrote up his last talk, given 2 weeks before he died. And he made a call, and this was the call he made about scholarly communication. We should establish digital libraries that support other sciences, just like the National Library of Medicine does for medicine, and I'll come back to that. We should fund the development of new author aid tools and publication models, and that's something really that the iSchools and the iConference surely must be looking at. And he felt very strongly we need to explore the development of digital data libraries that contain not just metadata, but also contain the actual data, which is curated and actually has a preservation mechanism to do it. And this must be integrated with the published literature so you can go from the paper to the data and so on. So that was Jim's call to action. And his vision was, in the end, that the world and science and indeed research will be just one gigantic digital library, all scientific data online, and you could information at your fingertips everywhere. The cloud will enable you to access this from wherever you are on the planet. You'll be able to get your work environment wherever you are and take it with you. So this was Jim's vision. So I would just like to say in my last few minutes where I think universities and perhaps high schools actually should fit in here. I was the Dean of Engineering at Southampton. I was a professor for 25 years there. I'd like to tell you some of my experiences with the library, of which I was a supporter in general, although I didn't agree with the librarians' insistence on expanding space for shelving. That seemed to me unnecessary. And a few other little things. But nonetheless, I think that we have evolved. So this is PubMed Central. What is PubMed Central? It's now a legal requirement if you get funding from the National Institutes of Health that you deposit. You can publish wherever you like. Could be in Science, could be in Nature, could be whatever journal, PNAS, whatever, PLOS. But you're required after, I think it's 12 months, that you have a full text of copy available in PubMed Central that anybody, you, me, our taxes have paid for this research after all, we can all access this research. And that's the principle of open access. And in this case, PubMed Central embodies that and the publishers have complied with it. But it does more than that because there's also databases in this sort of walled garden of the National Library of Medicine. And what the tool like Entree enables you to go from a paper to the data contained in the paper, look at other data, go back to other papers, and you can do this sort of search. And David Lippman, who is at NCBI, which is responsible for PubMed Central, believes that he can sit down with a medical researcher for a couple of hours and actually help find us a new discovery by navigating all this data. David Lippman's one of the most published medical researchers. So this is an example. This is an example which is well funded by the federal government. Not all fields are going to be able to have a centralized location. So we also, I think, have to consider federated systems and how could those come about. Well, as Dean of Engineering, I was responsible for monitoring 200 faculty and about 500 postdocs, grad students. So a large number of people producing lots of stuff, and I'm supposed to be responsible for their research, to monitor, see what's happening. And since the library could no longer afford to subscribe, every year we've got to think, which ones do you want to cancel? That's typical. And furthermore, if I wanted to start a new field of nanoengineering or whatever, you couldn't subscribe to new journals because there was no budget. So the whole system was clearly broken, all right? So what we insisted was that we keep a digital copy of everything anybody produces, be it a research paper, research report, thesis, PowerPoint presentation, data that goes with it. So we set up an institution repository. And the person who did it, incidentally, was my wife, who is actually a real digital librarian, unlike me. I steal all her stories. Right? Okay, so this is an example of open access. It's green open access. Most publishers will allow you to put up some version of your paper on your website, the departmental website. You have to read the small print, and maybe they don't allow it at all, in which case you keep it internally. You don't let it be viewed externally. But you produce this stuff. You were paid to produce it. You have a right to keep a copy. All right? And that's what we insisted on. Okay, so that's what that said. So it isn't necessarily the final version, but it is a version that people can see. And that, I think, is important and powerful for the following reasons. This is an example which still amazes me from Virginia Tech. I'm sure most of you know it. Electronic theses and dissertations. In 1997, their Dean of Engineering insisted that they keep a digital version of all theses and dissertations, master's theses and PhD theses. And in 1997, you had 200,000 requests for PDFs. And in 10 years after it was put up, you have over 20 million. I do find that surprising. Why do 20 million people want to look at Virginia Tech's theses? But apparently they do. So what it illustrates that having things available, having things accessible, makes people be able to find it, they can use it, they can access it, and makes your research much more visible. Another example, which is a result of the repository we put up. Now this is, there's various rankings of universities. I'm sure you're aware of that. There's a Shanghai ranking, there's a UK Times ranking of world universities. There's also this thing called webometrics. Now, I don't subscribe to webometrics methodologies, but I'm just looking at one of their criteria, which is what Google Scholar says are the number of papers you've got there and the citations. So they lump all this together, and then they rank universities by the Google Scholar hits that they get. Now, this is the result you get. If you look at other things, you'll see a different list. But here, it's not so unreasonable. Harvard and MIT and Stanford are up there. But there's a few oddities. One of the things that Southampton is clearly better than Oxford and Cambridge in the UK, which I know is not true. But nonetheless, our research is more visible, and people can see it, and people cite it. So having your research up there visible is actually something to do with the reputation of your university. So it's reputation management, and the research repository, I think, is important. This is not a perfect metric. We can do better. You can do better. You devise whatever metric you like, but certainly measuring the visibility and how often it's cited of your research papers is something of relevance. So what's the future? Well, it'll not only have the full text versions of research papers and grey literature, but also it'll contain data, images, software, and so on. And what you need are federated databases and being able to search across these. And I think this is a big opportunity for major libraries to play a major role and partner between them to look after the data. So we've seen the example of a centralized one. There's also Worldwide Science, which we had an ICSTI conference this week, and they have a Worldwide Science where they access databases from something like 80 countries now, I think it is. And they have a translation service, so you could type in a query in English and it goes to a Chinese or a Russian database, is translated, and then you get the results back and it's translated back. So these are some examples. And there is, if you're interested, in Europe there's much more emphasis on repositories, and there's the Coalition for Open Access Repositories, and it's very difficult, for example, to find a US university on that list. Where's the future? Well, I think the cloud is going to be part of everybody's future, and cyber infrastructure, a vision where you have some of the services locally. You may have copies of the data, you may have part of the data, but you may have access in the cloud, you may have compute services, you may have storage services, you certainly will have identity services. We already do have that. We have blogs and social networking. So a mixture of resources, local and in the cloud, will, I think, be part of the future. What about the library future? I'd just like to end with this comment from Paul Ginsparg. He created the particle physics archive called Archive, which everybody uses. Every particle physicist, every physicist and astronomer and mathematicians, every morning they go and look at what's been newly put on Archive, rather than the archival papers that are published. So he says, on the 1 decade timescale, it is likely that more research communities will join some form of global unified archive system without the current partitioning and access restrictions familiar from the paper medium, for the simple reason that it's the best way to communicate knowledge and hence to create new knowledge. And secondly, ironically, it is also possible that the technology of the 21st century will allow the traditional players from a century ago, namely the professional societies and institutional libraries, to return to their dominant role in support of the research enterprise. And I think that's a noble vision. Thank you very much for listening.
Are there any questions for Dr. Hay?
Just before coming here, our faculty had a very interesting email discussion about a repository that the library at our university is trying to get off the ground. And the discussion was about central repositories versus the local depositories of, universities like Virginia Tech that you mentioned, or the Med Central repository that you're talking about. And the question is, if you have a central repository with all of the researchers in the world know about, why would you do a local repository, for example, right? And then the challenges of managing all of the publications from all your institutions and make sure that they are up to date and that people have access, and of course, the fight with the publishers when they don't want you to put them up there.
Okay. The question was, if I summarize it correctly, should we have a centralized repository? What's the point of having local ones if we have a big centralized one? And what about the publishers? Well, the point is, I don't know what should replace them. I edit a journal for Wiley, right? So in interest of full disclosure, I don't wish to put publishers out of business particularly, but I do know that the present system is broken. And I don't know what's going to replace it, but it's clearly ridiculous that, they get all the material electronically, and now if you want a paper plus an electronic version, they pay more. The prices have gone up 10% for the last 15 years. Library budgets haven't. Something's got to break, and I don't know what it is. So I don't want to put them out of business, but things are going to change. So I'm going to put publishers to one side because we're in the midst of a revolution. What about centralized ones? Well, even if you have a centralized resource like National Library of Medicine, my wife worked on a project on oceanographic data in Southampton, and there is a national oceanographic archiving service in the UK, and they take some of the data, but there's always other bits of data which are not taken, and I think that the institution has a responsibility to do that. And I think, my students never went in the library for doing research type things, engineering students. They went there because it was a warm place to work, they could get Wi-Fi, they could chat to their friends, but that's confusing a library with Starbucks. All right? And actually, what's the purpose of a research library? Well, actually, it must be to work with the researchers you have to guard the output of the institution, and similarly with the teaching role. So libraries need to reinvent themselves to be relevant. And I see that you will need, yes, you may have centralized ones, but it won't contain everything, and the universities must be responsible for what they have. But I do see the possibilities of federations of major libraries, for example, in the US, where they have a lot of resources. The resources are already there, and they have money. The money at the moment just goes to the publishers, but it'll change. I don't know how it'll change, but it will.
One more question for Dr. A, please. Yeah.
Just a quick question. You had mentioned, or maybe somewhat of a comic-sized question, you had mentioned the theses and dissertations, why it was confusing, why a lot of people would want that. And I know from a lot of my research is on cyber victimization, and that's a very evolving, especially in relation to disabilities is what I look at. The intersection of those two is very much evolving. I like to cite sometimes some dissertations because the latest is sometimes being done by grad students and is not yet out in a journal. Sure. And it seems like dissertation theses, even more so, are walled off than the journals, because ProQuest kind of keeps them behind this walled garden that you can only often get in your own university, unless you're at like Virginia Tech or some other schools. Now, do you see that changing also in maybe the next 10, 20 years, where they have an open library where all the dissertation theses, instead of sitting on a dusty shelf, are the PDFs which are already out there that are just sitting behind ProQuest's wall can be accessible to researchers, because that would benefit, I know, a lot of my research.
Well, apart from PDFs, I agree with you, right? I think PDFs, actually, you lose a lot of the information if you lock it up in a PDF. Okay. But yes, my son just finished a PhD at Berkeley, and I said, you've got to make your thesis available online. So he said, I want to do that, and they said, okay, it'll cost you $80, and you have to pay for it. And I said, this is ridiculous. I talked to ProQuest and said, oh, that's surprising, because we only charge Berkeley $50. So Berkeley were making a profit. Some numbers like that. Anyway, but that has changed apparently. So what he did was put it up on his website. So I do think that universities need to be more proactive, and I agree with you. This is where the latest research. Last example, then I'll get off the floor. I came from particle physics, where we had this preprint thing. So archive is an example of instant research. You can find out what's going on. In computer science, we have a very strange system that our journals take 2 years to accept a paper, and it takes 2 years to acquire some hits. So if you want to find out what the most significant paper was 4 years ago in computer science, you can find out from Web of Science. But if you go to the astronomers, you can find out what the most significant cited paper was on black holes last week. because it's all accessible. And I'm absolutely sure that what Paul Ginsberg said at the end, you know, is this the way to do research better? So I think it will come, but I think it's this community is going to help change the world. I don't know where it'll go quite, but I think it's your job to find out. Thanks very much, Lee.
Thank you very much, Tony. Our next speaker, make sure my mic is on. Our next speaker is Curtis Wong, principal researcher on the eScience team, actually in Tony's organization. But Curtis has been with Microsoft for many years, and has done some amazing work, a broad variety of different projects. And every single one of them has been a tremendous, in and of itself, a tremendous achievement. Most recently, he's been working on, with a couple of other colleagues, on Worldwide Telescope. And I thought it would be very interesting to have Curtis walk you through through that tool and through some of the latest developments they've done with that. So I'll hand it over to you, Curtis.
Thank you, Lee. So a little bit of history. Tony was talking about Jim Gray. Well, about 9 years ago, Jim and I met and talked about a project he was doing around the data from the Sloan Digital Sky Survey. And they were thinking about creating a site which ultimately became SkyServer, where they would bring together all the Sloan Digital Sky Survey data and make it available to everybody, essentially the first sort of public astronomical data archive. And I went to him, I said, you know, having the data available is great for researchers, but there's also another opportunity, I think, to really inspire and educate people. I think having the data there, the imagery there, is a great start, but what I'd really love to see is I'd love to see a really rich visual environment that essentially emulates the night sky, where kids and that live in major metropolitan areas, like I grew up in LA and I never saw the Milky Way, and 70% of kids live in major metropolitan areas, can be able to start to explore the night sky and to be able to see everything from the broad swath of the sky to the highest resolution imagery. And not only that, but I also wanted the opportunity to be able to hear from astronomers about what it is that they're seeing, because everybody's seen these beautiful Hubble images, but most kids have no idea how big that is or where it is in the sky or really what's going on with it. So part of this was, you know, I made a pitch to our VP of research at that time. I wanted to build the biggest telescope on the internet, and he says, well, I'm not quite sure exactly how that's going to help Microsoft business, but, you know, we're in research and I'm looking forward to seeing what you're going to do with this. And so we started this project about 2006, and it started with me and developer Jonathan Fay. And so what I'm going to talk about a little bit today is take you a little bit into Worldwide Telescope, probably show you some things you may not have seen. How many people have seen Worldwide Telescope? Oh, not too many. Excellent. Well, maybe you'll be surprised. So I'm going to go into Worldwide Telescope, and if you don't mind, I'm going to turn the lights off since we're going to be looking at the night sky. And there, maybe you can see that. So this is the Milky Way in visible light. This is the largest continuous color image of the visible light of the night sky that exists. It's a 1 trillion pixel image, so you can seamlessly go right into the center of a galaxy. And in addition to the visible light view, we have the ability to look at the night sky through microwave, the dust, the hydrogen, essentially 50 different wavelengths of light in the night sky. I could pick this as a foreground layer, and this is a supernova remnant. So if we zoom into this supernova remnant, you can see the signature of that. But if I go back and crossfade, I can see the visible light view behind it and see the debris clouds from the result of that supernova remnant. And this was actually one of the important principles that we wanted to do in bringing this all together, because in astronomy, much of the imagery is sort of contained within the different silos of the particular survey. You know, the Hubble concentrates on visible light, the Chandra on X-ray, and the Spitzer on infrared. And how do we bring all that together to provide sort of a larger context for a lot of this imagery? And within the capabilities of Worldwide Telescope now, we have the ability to bring in, you know, astronomer can have their own images displayed on the sky at the exact right location so that they can, again, compare something that they're looking at across other spectrum. You can also look at other image studies such as these from the Hubble, and we have many, many of these. If I clicked on M42 up there, I notice that's off the screen. So down here on the lower right, you can sort of see that blue rectangle, kind of like powers of 10. We're giving you a sense of scale and where that object is in the sky, in the celestial sphere, and what the field of view is. And because these are very high resolution images, you can continue to zoom in right down to this little black grain of rice, which is an edge-on view of a disk of dusk, which is forming into a solar system, and a star is being born at the center there. So I mentioned before the idea of these guided tours. And so guided tours are being produced by kids, by educators, by professors and astrophysicists, and there are different categories of them here. Here's one that's done by a 6-year-old, right next to one from Harvard University. And this is
the Milky Way is a spiral galaxy, but it's hard to see that because we're inside it. Here's a spiral galaxy not far from us, about 12 million light years away, called M81. If we look at it in optical light, we see billions of stars shining together in a spiral pattern. If we look at the heat from M81 rather than the light, it looks like the false color orangey image we see here. This Spitzer Space Telescope image uses long wavelength cameras that can see heat, just like the one that took the picture of this cat. Galaxies are filled with tiny particles called dust that absorb the light from stars.
So I can pause this. And even though it feels like a video, it has the text and narration and music, it's actually just a path within this visual and data environment that we have. So if I wanted to see what the context of that image was, I could zoom back out. If I wanted to see what that image looked like from the Chandra X-ray telescope, and there are many sort of other contextual images that would overlay that particular object, you can see it. If I wanted to branch off to a different tour that talked about the interaction between this galaxy and a nearby galaxy right there, M82, we could do that. But another really important capability is that behind every object, I can right-click and pull up a little information window where I can say, if I'm a kid doing some research on a paper, I might want to look in Wikipedia. Or if I was an astronomer and wanted to find out what's the latest paper that was written that cites this particular object in ADS, which is the Smithsonian Astrophysical Database. And here you can see it did a real-time query that found 2,625 papers, of which the most recent one was last month. You could also get original source imagery. As I mentioned before, a lot of imagery was contained in the specific telescope areas and different servers, and if I wanted to find a DSS image, I don't have to know where the database is of the query. I can just say, go get that image for me, and it would bring it right here for me. I could get science level imagery as well. So in addition to this particular rendering of the image environment, we also have a full 3D model of the solar system that goes all the way out to the local universe. And you can sort of see the orbit of Pluto right there. And we could go right into an individual planet, but in the interest of time, I'm going to go back out a little bit. Here's the constellation Orion behind it. If we pull back away from Orion, you'll notice the local stars in our arm of the Milky Way start to change, because if you look out this way, you can see that the constellation, the stars in the constellation Orion are actually at different distances. As we exit the Milky Way and go out into the Sloan Digital Sky Survey, these are the million galaxies from the Sloan. Essentially, the 3D manifestation of the original work that Jim Gray was starting to do back in 2002 with Alex Illey and that team. But even though this is a really interesting visualization, it's actually a connected view, like we were talking about earlier. If I wanted to know what was behind that particular galaxy, just to randomly pick one, we go right into the Sloan site. Here's the image of the galaxy. You can see the redshift. I can download the data for that. I can pull up the spectra for the chemical composition of it. It's all right there. So one other thing I'd like to show you is the more recent work is around bringing in data within this particular space. And to do that, we'll start with something a little bit more familiar, which is around the Earth. So I'm going to go over here and bring up the Earth and dock this over here and bring up some data. So here's some data in Excel. It's of earthquakes from the year 2002. So you can look here and see that there's about 40,000 rows of earthquakes here. Kind of difficult to comprehend given the amount of information in there. But what we can do is we can bring that data into Worldwide Telescope, I can bring up a layer manager here, and you can start to see what that data will look like. Here we go. So here's 40,000 earthquakes in that particular year. Now we can play around with some of these properties here by perhaps changing the scale of them so we can see them a little bit more densely. But you start to notice we actually have depth data in here. And you're starting to see these weird clusterings of the earthquakes happening in the middle of the ocean. But if we pick a different underlying image layer behind it, you can start to see the context of that, in that a lot of these quakes here are really in the subduction zones between ocean and other plates. Now, we have data in this environment. One thing we'd like to be able to do when you have lots and lots of data is to be able to annotate them fairly richly. And so within Worldwide Telescope, just like the tours you saw earlier, we can create tours that are essentially within this environment that can help us take a look at data in this particular space to call out interesting anomalies. So I'm going to take this particular tour here and open it up. And I'm going to play it. So I could easily be annotating this with some talk about what it is that people are seeing or something that I wanted to call out. I could add in any kind of graphical elements. Any element that's in here, I can have it linked to a website outside or some other data source. So you can imagine when kids see something like this and you start talking about earthquakes, it becomes very, very obvious about some of the things that were happening. We just saw the area of Seattle about what Tony was talking about earlier. But here, of course, you can see the clustering of earthquakes along that subduction zone off the coast of Central America. And so even though this is like a video in a sense, we can compress time. And we're just looking at those 40,000 rows of data over about 10 or 15 seconds. But these tours are also fully interactive as well. You can sort of pause and explore because you're essentially in that data environment. I could hover over any of these data points too, and you can start to see the metadata about that particular quake. And here's the coast of Chile. All of its aftershocks. So I'm going to show you one more thing, which is another tour, which is actually a tour that was created by Harvard in commemoration of an astronomer named John Huckra, who worked with about many years ago on the large-scale structure of the universe. And what's interesting about this particular tour is that it's a very, very rich data tour within the environment, but everything that's in here, they mention things like papers and other things. Every paper, everything there is linked to the original paper. So while you're getting the story of John Huckra's work, you can pause and drill into all of the underlying material related to the data and research around what John Huckra did.
Or where the galaxies were in that stretching space. Lucky for us, John Huckra saw our ignorance as a fantastic opportunity. As an astronomer, his principal goal was to learn the three-dimensional distribution of matter in the universe, much as we know and understand the surface of the Earth. Here is a three-dimensional view of the top of Mount Hopkins in Arizona, the site of many of John Huckra's astronomical observations. Adding altitude measurements to a two-dimensional map of this part of Arizona gives a 3D view. In the same way, adding distances inferred from galaxy redshifts to a two-dimensional map of the sky can make a three-dimensional map of the universe in this diagram.
So I'm going to jump.
It shows galaxies of the slice.
This is their
projected
first
to make a
survey they plotted
two-dimensional
against
view.
the sky. So this is real data plotted against the visual imagery of the Worldwide Telescope.
It's easier to understand this diagram if we look at it in context. So let's put it there before we dissect its meaning. Shown here again are the galaxies in the first strip as projected on the sky in 2 dimensions. If we color code the same first strip galaxies in a 3D view of the universe given to us by the modern Sloan Digital Sky Survey, we can see how a strip on the sky translates to a wedge in 3 dimensions.
So you can see the scale of it is much smaller than the modern-day Sloan study. So I'm jumping to another part of the tour. So these are the 18,000 galaxies of the CFA2 survey, which are color-coded and plotted in the sky, color-coded by the redshift of that particular galaxy. So again, this is a fully interactive experience in that you can get to any individual galaxy behind each one of those plots and see the underlying redshift behind it.
John Hooker was...
So that sort of gives you an idea of an example of that. And I want to make sure that we have time for questions. So I'm going to go back here. But I think thinking about big data and the opportunity around big data, particularly around astronomy, I think some of the opportunities are, first, making the data available and making it broadly available to the public. The second is bringing together tools that are really simple and intuitive to use for the public to have access to that data, allow for rich annotation, and a collective way to sort of surface it and make the feedback connection back to the scientists to sort of to make them aware, kind of like what happened with the Hannes Oort cloud, which you may have heard about, where a Dutch school teacher identified a new object in the night sky. So anyway, thank you.
Thank you, Dirks. Maybe a question or two for Curtis while the next speaker comes up. We do have a question. For a second, I thought you were stunned into silence after that demonstration.
Thanks.
So thank you very much for that for the presentation. One of the issues that I think all of the visualization that you've shown us today raises from a science perspective.
Mm-hmm.
You can do the visualizations, but a lot of the predictions, for instance, the National Science Foundation is fast-forming teams for research in distributed modes,
mm-hmm.
and the collaboration aspects, trust aspects of these scientists who may
Right.
not fully know each other
Right.
in human dimensions.
Yes.
So
how do you contain that?
Yes. So how are you thinking about how that all plugs into this? Because e-science won't be successful without this kind of fast-forming team.
Right, where sort of the integrity of everybody that's involved in the early stages of science. I mean, I think what Alyssa is doing with this, who she did that earlier tour, is she has her data sets, and she can publish these paths and annotations about her data sets in this environment that are, of course, private. Because what I showed you in these tours, they're just a stream of metadata, a relatively small path that shows it's access to the data as well as these paths in the data as well as the rich annotation about the data. And then she can share that with a number of her colleagues, and then they also have access, takes them to the data, and it's contained within themselves. And so when you're ready to publish, it's sort of a different story of how you then sort of make something perhaps a little bit more analogous to the last thing that I showed you, and perhaps that's an idea. I'm not saying this is the solution, but I'm hoping to try some of these new ideas and see what people think, and hopefully it will inform the process a little bit. So, another question.
Accessibility, you showed some examples of videos from someone from Harvard and then someone from elementary school.
Yeah.
All right. So and it looks like a pretty complex interface in general. How accessible is it, and who, to, I guess, people with varying skill levels and talents, right?
Right. Well, if I had time, I could show you. The authoring is built into Worldwide Telescope. And it's very analogous to PowerPoint. So all you're doing is, if you can see something, you can create a slide, and it's the starting point for that. And if you go somewhere else, like if I zoom into a portion of the sky, you just say, the end should be right here, and you've created a camera move into that space. Then you create a new slide, and then where you go from there, and then it interpolates to the next space. And then if you want to add narration to it, you just can click and say add narration, and you can drop in an audio file. And it spans across those things. So a lot of the things that you've seen, like the kids tour, is just him narrating these little places that he wanted to go. And the thing you saw with data is a bit more complex. Of course, you have to bring data into it, but it retains sort of the meta about that data when you're creating it. I hope that answers your question.
Yeah. So would you say it is accessible regardless of?
Oh yeah, it's accessible and it's free. It's at worldwidetelescope.org. So it's a free resource. Thank you.
Right, well, please join me again in thanking Dirks. And next, I'd like to introduce my colleague, Donald Brinkman. He's actually from my team, and he's going to be showing a demonstration about something called Chronozoom and a little bit of the work we're doing with big history professors from around the world. Donald.
Thank you. Hi, everyone. So yes, my name is Donald Brinkman. I work for Lee. This is an excerpt from a longer presentation. It's going to be more about the big history and the deep zoom than the long tail. And let me just jump into it. So first of all, I just want to kind of give a little context for what we're talking about today and just talk a little bit about big history. This is probably the most words you'll see on any of the slides I'll show you today. I've tried to give you something nice and light for after lunch. Big history is a field of study that looks at history in a context larger than just human history. We look at Earth history, life history, and the history of the universe. So how did Microsoft get involved with this? There's this guy, his name is Walter Alvarez. He's pictured here. He's the strapping young lad over there standing there. He's holding this little vial. The vial it's full of iridium, and he's a geologist. And he's very well known for the fact that back in the 1970s, he was part of a team that was looking at the KT boundary, which is the boundary between the Cretaceous and Tertiary layers of the Earth's crust. And he found these high levels of iridium in this boundary. He made this hypothesis that the reason this was here was because there had been a giant asteroid impact. And there was another interesting quality of this space that on the Cretaceous side there was lots and lots of fossils, and on the Tertiary side there was very little. And so he came up with this hypothesis that the dinosaurs had been made extinct by a giant asteroid impact, which at the time was considered to be an insane thought, and no one believed him for about 10 years or so, until we found a giant asteroid impact dating exactly to that time that had a whole bunch of iridium in it. Walter was validated, and he went on to continue teaching at Berkeley to much acclaim in his field. Fast forward about 30 years, and we have just last year Walter giving the 97th annual faculty lectures at Berkeley, which is one lecturer is chosen per year to give a sort of capstone lecture. And you can see here that in his talk he's talking about big history, and he credits Microsoft Live Labs and Microsoft Research, and that's what I'm here to talk about. So Walter, maybe about 4 years ago, started getting interested in big history, and he wanted to teach it in his classes. And he wasn't sure how to go about doing it. Now, I mean, he knew how to talk about these things. He had a wonderful resources at Berkeley in terms of people from all sorts of different fields to come in and give guest lectures, but he had a real difficult time conveying timescales. It's very hard for people to viscerally understand what it means to go from human history to life history and then, Earth history and the history of the universe. And really it has to do with, he had this idea to zoom. So he asked his students, he said, how should we go about and do this? And one of his students, Roland Sakow, raises his hand and he says, well, why don't we just go inside of Photoshop and we'll make a giant canvas, this huge image, and we'll just kind of, click and zoom into it, and then people can see, what's going on, which is a really great idea. And Walter says, wonderful idea, let's go and do it. Very early on, though, they discovered this problem, and the problem really had to do with zoom factor. And the problem is that when you go from 13 billion years to a single day, you're looking at a zoom level of somewhere around 500 trillion%. This is a significant amount of zoom. And for all the wonderful things that Photoshop is capable of bringing to our lives, it only has a maximum zoom of 6,250%, which didn't get Walter and his team very far, although they did make an admirable effort to do it. We found out about this project, and Darren Green, who's the general manager of my team, he said, wow, this is a great application for this technology called Sea Dragon. Sea Dragon is essentially, it's this thing these guys dreamed up where they found that if you take a really, really giant image and you break it into what we call an image pyramid, so essentially you have a low-res version of the image, and then you cut that into 4 pieces, or a certain number of pieces, and then have the same resolution as you go down in it, the resulting total data storage of that image is about 1.3 times the original image. So it's fairly space conservative, and it also allows us to do some really amazing things with a little bit of animation and some seam stitching to create this effect of seamlessly zooming into an infinite canvas. And what I'd like to show you, I normally show an overview of there's a YouTube video that you can see if you search for Walter Alvarez or if you search for Chronozoom on YouTube. It's an hour-long lecture. I show a small excerpt from it. I'm a little time constrained, so I'm going to jump right into another video, and because I really want to show, in talking to Walter and his team, we discovered that not only did we give them the capability to teach big history in all its magnificence, and there's a working prototype on the web. If you go to chronozoomtimescale.org, you can go see it. But we also kind of made them into human interaction researchers. They started playing around with the ideas and what was available in thinking about education using Zoom as a metaphor. And let me just pull this up. So this is Roland Sakow. He's one of Walter's students who's narrating this, and he's going to show off an experiment looking at an Italy timeline and some of the ideas they've had about how to use Deep Zoom in teaching class and thinking about research as well. And I just need to figure out how to turn, there we go, I got it. Maybe. Oh, I got it.
Here we're looking at an example of periodizing history. In this example, we're using Italy, and the first big division you can see is pre-Roman Italy, and post-Roman Italy. So thanks to zoom technology, we can zoom into any one of these boxes to look at them in more detail. So for example, in Roman Italy, if we zoom in here, we'll see that's divided into early Rome, the Roman Republic, and the Roman Empire. This is just an example, so we're only providing one source. But in the future, we hope to provide different sources of different interpretations of history. Let's take a closer look at the Roman Empire. So what we've done down here is we've represented all the different emperors with little pictures or statues. So if we go into one of these, for example, and look at Hadrian, Hadrian is also a really good example of how there's really no limit to the kind of resolution that these images can be. So here's a quite large resolution image, which is really just a small part of this map here. And if we look over here, for example, here's a panoramic. Vesuvius. And these can really be gigapixel images. And that is, images that are greater than 1,000 megapixels, or 1 gigapixel. So, but again, that's just one small part of this entire document. Another fun thing we can do is we can embed papers. So if we look down here, we've got a paper talking about the periodization of history. This is an entire PDF, and any part of it you can zoom into. And you can do so without any delay of having to scroll, tediously through a PDF. And of course, one of the great benefits of figures, they remain sharp, but they're also very quickly and easy to browse, more so than using this in a standard PDF reader. High-resolution images, again, can take place. Here we are looking at an outcrop. And if we had a gigapixel image of this particular outcrop, we could zoom down right onto the ground and look at an object right on the floor. In this case, the marker. For now, though, that's just an illustration. And one last fun thing we can do, we go back in this paper here. Every paper has references. So here's the references cited of this paper. The tedious thing about finding the additional references, you have to first open them and download perhaps and open in its own reader. With zoom technology, let's say we're looking at this paper here, also by Alvarez. What you do is if you spy down here, you see that the entire paper is actually embedded right here also. So without any delay, we can keep zooming, and this is a full PDF in full resolution. We can look at any one of these diagrams if we wish. And again, we zoom out, we can see it's just a small portion. You can watch it there going away of the original document. And the original document is just part of this historical Italy example.
So I hope you can understand why I wanted to share that with you guys. I'm not saying that this is a good idea. There's a lot of questions to be answered about this, but what it does is it offers us, oh, that's not me. What it offers us is a vision of what's possible and the sorts of things that we can start thinking about if we start thinking about not just searching for documents, but thinking about semantic zoom as a method for exploring and researching. So that's the Berkeley Big History course, which is currently being taught this semester. There's an undergraduate course and a graduate course. The graduate course, we're actually working with a lot of graduate students to get data inputs for Chronozoom V2, which is what I'm really here to talk to you about. Before I get there, I'd like to just talk a little bit about this idea of search. And I really feel that I'm going to make a prophetic statement here and say that Zoom is the new search. And essentially what I'm saying here is not that Zoom replaces search, but in the same way that search became very important in the first decade of the 21st century, and we saw that with Google rising to its ascendancy in our culture, we're going to see Zoom take on a lot of importance as a complement to what search provides to us. And I see this when I go out and I manage our digital humanities programs, and I talk to a lot of people in humanities fields. And when I talk to people, I see, we talk a lot about books, and we talk about Google Books, and it's interesting because books are a really complicated technology, and they're very sophisticated, and they're very long-lasting. And we've actually developed these things called libraries, which are another technology that are composed of all kinds of other little pieces of technology, card catalogs, databases that help us to organize and access these incredibly valuable pieces of technology in our lives. But now what we have, with the advent of search, we've gone in this strange direction. We have this thing, it's the 10 blue links. I search for a book, and what I get back is, it's sort of like I'm teleported to an empty room, and there's the book, well, hopefully the book I wanted. And that's the thing, search is a little imprecise. It never knows if it got quite what you got. So what a search algorithm will tend to do, it'll give you what it thinks you want, and then it'll give you 10 other things that seem like very similar to the thing you want, in case those are one of those things. And this is neat, and it's very powerful. But when I talk to people, humanities researchers especially, one thing that comes up over and over again is that they say, I miss browsing the stacks. How do I browse the stacks like this? How do I have the sort of incidental discovery that occurs when I go in looking for one thing, and there might be something that is in a general coupling with this, but it's a sort of incidental discovery that I can't be enabled through search as we know it right now. And this is what we're trying to do, is in a sense think about semantic zooming and how we can enable a sort of matrix-like zooming bookshelf or multimedia experience. And so what we're working on now is Chronozoom V2. What we showed you, that image, and I do encourage you to see the full demo where you can zoom in from January or December 31st, 2000 all the way out to 13 billion years ago and see the entirety of the universe. It's really great stuff. But it's still a very primitive prototype. We're talking about, it's what we would call a raster graphic. It's a static image. If you zoom in on the letter A far enough, it'll become the size of the entire solar system and include all other data, which isn't that really meaningful to you. And so what we're doing right now is we're adding in significant additional capabilities. We're adding in scalable vector graphics, continuous algorithms, dynamic text and data, which what we're trying to do here is essentially provide these sorts of rich deep zoom experiences combined with visualizations of scientific data, continuously scaling algorithms, and dynamic multimedia from all kinds of internet data resources. Combining that with collaborative authoring tools, the ability to create tours in a very similar way what you saw in Worldwide Telescope, and rich multimedia experiences that are embedded inside of the authoring and presentation experience. And we're doing this, actually, I'm jumping ahead. See, I've edited my own presentation. I realize I have logical gaps. How are we doing on time? Should I? 3 minutes? Okay. So we want to do this to enable research, but we also want to do it to enable high school education. And there's a good reason for this. We found that with many of our most successful experiments, they're best if they have a higher education research application, but also a more common application. And you can see that in Worldwide Telescope, which can be used in astronomy research, but can also be used in museums, in libraries to teach kids about astronomy. In Chem for Word, which can be used for professional authoring of chemistry articles, but can also be used by high school students. And in the same way, we're really trying to look at this as something that can be incorporated into high school big history curriculums. And why? I mean, what's the point of this? I mean, one is that we can provide a more versatile tool, but there's other reasons too. If you think about this, and this is based on a little article that some of you might have seen on Gizmodo, if this is the whole of human knowledge here, so we have everything. Down here in the middle we have sort of that little nugget of elementary school. So this is basic literacy, basic maths that we all learn. If we surround that a little bit through high school, we have more common knowledge that we sort of join together. And then if we go into college, you get even more common knowledge and maybe a little bit of specialization. As you move into master's courses, you specialize even further, start reading journal articles. You get into doctoral work, and you achieve very highly specialized areas, and you start working on your dissertation. Eventually you push, and now you're up against the boundaries of human knowledge. You're pushing and pushing and pushing against those boundaries until finally at some point you break through. And that thing right there is your doctorate. And here's the thing. I'm not belittling doctorates, and if anything, actually I'm overemphasizing them, because I would say that this boundary here is logarithmic in nature. It's actually quite larger than just the sort of a linear progression here. This is a tiny little dot on this vast area that we're all working on. And when we think about how Microsoft Research makes its investments, we make point investments all over this boundary. And this is great. If your goal here is to advance human knowledge, then this is great, because we're trying to find the right places to go and make things, just push things forward a little bit. And this could be something, that is very, very specialized, or it could be something like a cure for HIV, for example. I mean, these things can be very important. But here, there's another way of looking at making investments in knowledge and education. So if we go back to education in high school, if we think about high school, this area where we kind of have a lot of people learning common knowledge, and we insert some big history, then what we can do is we can make 1 point investment that has the potential to teach an entire generation of kids a new way of looking at life, an empirical way of looking at life. Something that one of my favorite writers, Philip K. Dick, says is that reality is that which, when you stop believing in it, doesn't go away. Help people to really understand what is out there, what is real, how to try to understand things in an empirical sense. And I'm going to have to cut this short, because I could go, I got a little bit more? All right, he's going to give me some rope. I'm trying to single-handedly make up for our slippage in schedule.
I don't know. I think when cameras are snapping and people are laughing.
Go for it. I will do it. So just I want to talk a little about teaching and research, because we're saying here on the one hand we want a teaching tool and we want a research tool. How does that all work out? And so what we want is we want to make a tool for teaching, and this is how I tend to think of teaching. It's kind of like whitewater rafting. You can see some older, more experienced people out there in the back kind of guiding things down. We got some young and hopefully excited rather than horrified people in front, going down this we would hope to be an adventure and not a disaster. So, you know, if you look here, I love this picture because look at this kid, you know. I mean, this is like the natural love for learning that we should all have. And you know, and sometimes it seems like our school systems sort of turn this inside out, you know, and they provide a much different experience. And so you look at that, and here we have education, you know, and then you start to think about, well, what about research? You know, what about this as a research tool? Is that the same kind of experience? And sometimes we think of research in sort of a strange kind of way. We think of a guy, he's wearing, you know, last year's fashions. He's got some good technology, but it's sort of a monastic experience. He's by himself. But what I'd like to say is that ultimately, these two experiences don't have to be so separated. They might be right now, but they don't have to be. And one thing I talk about is games. Games is a really, you know, almost everybody plays games, especially now digital games are obviously getting a lot more, you know, experience out there. But these are things that go far, far back in time. Even now, like for a lot of people who are, you know, with work and students, people go home and they play video games after they get done with their real life. And many of us learn games from a very early age, you know, and it's a very collaborative environment at a very fundamental level. So what we're trying to do is create a more game-like, multimedia, exciting experience of education, but we think we can take that also into the research fields as well. So just to sum this up, I just want to say what Chronozoom is and what it isn't. So we're a platform to store and visualize timestamp data sets. We're an application for authoring interactive tours of these data sets, and a tool to compare disparate data sets and enable incidental insights. We really want to bring multidisciplinary knowledge into one place so perhaps a geologist can find out things about other fields like biology that they may not know of and find entirely new discoveries which could be meaningful to us. What Chronozoom is not is a platform for collecting and visualizing arbitrary data sets. We're really looking at a very specific application, looking at historical data in various types. It's not a platform for authoring, for publishing authoritative information. We see this as something that we imagine it in a classroom setting where a student could author a presentation and also watch a lecture. But it might be able to create some sort of visualization that could be put into something like, you know, a scholarly article, but it is not a route towards a scholarly article itself. It's not a tool to record timestamp data. So what we need is we need authoritative and seminal data sets from a vast variety of disciplines. And this is what I was trying to talk about at the beginning. We're working with Walter Alvarez and his graduate students to sort of bring together all these, like at least a seed set of seminal data sets. We're looking for novel visualization techniques. We're really building out a platform. The original Chronozoom was an end-user application. We're developing web services that will enable not just a single siloed application, but a multiplicity of applications that might surface in HTML5, Silverlight, you know, Facebook, iPhones, Xbox. It could be anywhere that has an internet connection. And we really need a passionate community that's interested in using Chronozoom as a tool for education and research. So we need you. And I hope this was entertaining. I encourage you to go out and check out the prototype, check out the YouTube lecture. Walter's lecture is an hour long, but it's thoroughly worth it. He gives a brief, big history lesson. And thank you very much.
Thank you, Donald. And I'd like to invite the next speaker to come up and maybe get set up. And are there any questions for Donald? I'll field one or two.
Maybe this is kind of a side question, but for Chronozoom, what are the storage capacity requirements for that? I mean, now storage is growing, but I wondered if there's any kind of limits and boundaries, because it seemed like when you're zooming and having all these really great looking images, and I know Vector is going to help with that, but it just seemed like, you know, even when you have videos and complex games, I mean, they take up a lot of space. So is that any challenges that you foresee now, or you're kind of really hitting that head on, and that's not going to become much of a problem?
So it's a great question. A lot of the data sets we're looking at are actually, especially as we go further back in time, are actually not that big or not that dense. It's really just being able to put them in context, which is sort of a big challenge. Now that being said, yes, there's tremendous multimedia out there, right? I mean, if you have these gigapixel images, the original Chronozoom, being one enormous static image, is very huge. What we're doing is we're developing new technology that allows us to actually dynamically generate image pyramids on the fly using this abstract data. So you could think of it as streaming a very efficient way of streaming particular data, and we'll cache it a little bit. So if like a lot of people are using the same data over and over again just for efficiency's sake, but a lot of this stuff is sort of exists in an abstract logical space outside of, yeah.
Any other questions for Donald? All right, we're letting you off easy.
All right.
Thank you very much.
Thank you, guys.
I would like to introduce Andy Wilson to be talking to us about a lot of his research with touch and human-computer interaction. Andy is, I'll call you this, you may not claim to be this, but Mr. Surface. He is the man responsible for that fantastic interface. So with no further ado, we'll hand it over to Andy.
Thanks, Lee. My name is Andy Wilson. So I've been doing a lot of projects around Surface and Connect and depth sensing, cameras, and fundamentally new ways to interact with computing. And what I'd like to do is show you a couple of videos of some of the things that I worked on, because I think that rather than sort of giving you a bunch of PowerPoint, I think that actually speaks better to what I do. And they're a lot of fun to look at. And you know, there's definitely a theme, but I'm just going to kind of hop through. Okay. Is that better? No? There we go. It looks like it just came on. Thank you, whoever did that. Yeah, so I like to build prototypes, working prototypes, as a way to investigate whether or not an idea works. So we spend a lot of time building systems. And I just went through my collection of videos and I pulled out some things that I realize now that I really like. And some of them are actually getting a little old, but I think are still fun to show anyway. So as Lee mentioned, it had some role in the development of the Surface product. And some of the things that I'm going to show you today are actually riffs on that, or things that we were doing at the same time that we were developing the product, different kinds of interactions, different fields, things that you don't see in the product but are still nonetheless interesting. This is a networked version of two Surface-like units where we use top-down projection. And I think the thing that's really interesting about this is that well, you see the other person's hands, but there's no, unlike most teleconferencing scenarios, there's no buttons or icons or menu. This is just like a video conferencing for your desktop, if you will. And so you get this sort of interesting effect where it's very analog. It's a very analog experience. And I think that that's actually a theme that's starting to come out of all of the things that I do. I didn't realize this until a few months ago that this is kind of what I like. So having this sort of analog experience. We're using these very digital systems, very powerful sensors, video cameras, and interesting sensors and phones and so forth. And at the end of the day, we're recreating some of the things that we do already in the real world, a very analog experience. Of course, it's a little bit different. The person's not actually sitting across from you. We're stabilizing the background here, or the actual chessboard. That's really the only sort of smart processing we're doing with this. But you get the sort of intangible quality of the user's gestures, maybe some of their thinking. You can imagine coupling this with a more traditional face-based video conferencing. Here's kind of a fun one. Instead of having the person come in from the opposite side, you actually have them come in around you, if you will, or from the same side, like that. And so you get a very different kind of feeling. And when I first did this, I thought, oh, this is going to be really strange. It's going to feel like this person's violating your space when they come in. And really not a concern. Something you get used to right away. The funny thing about this is that when you're done making this drawing, of course, you don't actually have a drawing. You have exactly half a drawing. We could rectify that in software. That's not a real problem. Here's another one that I really like. This is something that we've been picking up on, and actually, I think we're going to see this become more pervasive in real products before too long with NFC and all the kinds of other standards. Put the phone down. System identifies the phone. It finds it does a handshaking over Bluetooth and then pulls over your camera phone photos. Right? When was the last time you thought, oh, I'm going to transfer something to my friend using my phone, and then you realize that there's this kind of impossibility to it because it's so complex. If you could just put it down on a tabletop, your buddy puts down their phone and you just drag from one phone to the next, and you break the connection by picking up the device. That's something that I think is magical and makes a lot of sense. It makes The idea being that let's make the user experience so easy that you actually start thinking, oh, I can do these kinds of things effortlessly. This is just a little detail. This is what the camera sees above the surface. You can see that this is actually picking up an infrared signal off the phone. This is done in the days when we had IRDA ports on our phones, if you remember that. There are other ways to do that now, NFC, near field communication, being probably the, one of the front runners. Another direction of my work is just thinking about completely different interaction modes, different ways to think about. We're all used to cursors, right, and pointers, and multi-touch is just multiple cursors, really. This system is a surface-based system where we think about how can we leverage the full fidelity of the input. Surface is all about using video cameras to detect what's going on, detecting shape, making use of shape. And the way what we do here is actually bring all of the input, all of the data from the image into a physics engine, a real-time gaming physics engine. Things move because we're simulating friction forces and collision forces. So if you have any experience with video games, you know that objects tend to behave as if they're real-world objects, that things collide, and there are sometimes even friction forces simulated. That gives you a different feel for interaction. Here's just a really simple demo that I think says it all. You can lightly touch this ball to influence its direction, or you can trap the ball with your hand. You can spin it. You can set the moment of inertia, the masses, the friction coefficients of friction, dynamic and static, and just completely change the behavior of this ball as if it were a real object. Stacking objects is kind of a fun thing. This is a 2D, a projector showing a 2D image, but it's rendered in 3D. It looks really 3D, and it sort of almost feels 3D sometimes when you're interacting with it. It has a very different feel. Because we're using a physics engine, we can do all sorts of fun things with simulating cloth, different kinds of things that you may have never really interacted with before on a touch display. And again, leveraging all the kinds of expertise that you have interacting in the real world. I'm going to skip ahead just a little bit. There's some kind of funny little demos that we've been playing around with, just pushing the limits of what we can do. We can't really do origami with this system. We can do a single fold, and then that's pretty much all we can do. And then tearing. This is a fun one. When you're doing this, there's almost a kinesthetic quality. It's a little hard to see this. There's almost a kinesthetic quality to it. You really do feel like fruit roll-ups. Remember fruit roll-ups? That's what it feels like. Even looks like a fruit roll-up a little bit.
Turn the lights down.
We can turn the lights down back there. I'm going to skip ahead. I'm going to give you a little bit of a peek. Excuse me. As to how this actually works. This down here is a representation of what Surface sees after a bit of filtering. And then what we're doing is bringing in these red objects. These are actually rigid bodies that are being manipulated in the physics engine. And so these look rather different than cursors, right? We're actually throwing down as many of these little red objects as we need to approximate the contours that we see in the image. And so we never had to decide about what makes a contact or what makes a cursor. We just put it all in there and control it appropriately. So I mentioned at the start that I've been involved with some depth camera technology. This is actually one of the very first systems that we did at Microsoft that used depth camera technology. The camera here is made by a company called 3DV, which Microsoft acquired a couple years ago. So we combined this with a projector. There's the projector sort of more or less in the same place. And then these little cars here they are projected, obviously. And then you can drive them around with an Xbox controller. Okay, nothing unusual yet. Okay, then you put down this piece of construction paper, and you can drive the car over the construction paper. Right, and so the car takes the jump appropriately because there's a physics engine running behind it, this all. And basically this is the view from the computer. This is how the computer sees the world. We're getting the range map from the camera. Now things are a little bit soft and fuzzy because you have to do a lot of smoothing to make this really work. But the system doesn't know anything about red objects or construction paper or these ramps. It's just taking the color data and the range data to build up this little course. That's basically it's something that you put together. And I'll show you in a few minutes here that you can actually do some things with your hands, which is kind of exciting. This is the view again from the computer's point of view. This is just an exploration into extending the boundary of what we know with regards to surface and sort of how we think about surfaces. What if you really did know something about the objects that are on top of surface in a real, tangible way? Yeah, this is sort of your arcade view. I mean, once you sort of get into this sort of mindset, you start thinking, oh, this would be really cool if I do this, and you do this game, and you kind of go nuts with this kind of stuff. It's really, now you might understand why we have to do so much smoothing. Like a little bit of a noise in this creates a giant pothole and gets really difficult. Here's a little bit of interaction where I'm actually reaching into the scene and dropping these blocks by this pinching operation. The pinching operation, there's the, I'll come back to that later. Here is the 3DV range image. Brighter things are closer to the camera in this image. It's rather similar to what Kinect gives you. Kinect's data is actually rather cleaner than that. Here is me driving the car up onto my buddy's hand, capturing that, and we actually took the system to the Maker Faire a couple years ago, and it was really fun to watch. I had all the 12-year-old boys in the crowd, completely mesmerized. They were fighting over who gets to drive and who gets to knock the cars off the table. This is again the systems view. Now, of course, it's really not a 3D camera. It's more of a 2.5D camera, right? You can't see around objects with a camera, right? So you get the sort of effect that's almost like you threw a bedspread over your desk, right? And you're working with the resultant shape. Yeah, and there's the same thing again. So you get this kind of weird effect. So that was some really early stuff. I guess we did this in 2006 already. Shortly thereafter, I did a little bit more work on this physics part of it, and just started thinking about, well, what more can we do around looking at hands and physics models, getting a little bit closer. This is now the PrimeSense camera, which is actually the camera that's in the Kinect. It's an early version of Kinect, essentially. And the thing that I really like about this is because you're using the depth information, and you're using a lot of the depth information, almost all of it, in fact, you get all the fidelity, all those sort of weird shapes in your hand, and sort of the way that your hand sort of falls off as you go sort of towards your fingers, and sort of all these things that you actually really have internalized over the many years of being a human. Why can't we use that today in our interfaces, right? The subtlety of human motion is brilliant. The way that you grasp objects, the way you pick up objects, these are things that we completely ignore when we're just talking about a mouse and a mouse cursor, right? And so I believe that with some of these interesting kinds of sensors that we're playing with now, we can actually get back to some of that fidelity, some of that subtlety. This is a project that we recently completed, I guess this past year, and what we did was ask the question, what if we took 3 or 4 of these Kinect cameras and actually covered the entire space, the entire room with these cameras? And so what we did is we built like this kind of chandelier almost. So we have these 3 projectors. These guys here are these cameras. Those are PrimeSense cameras, again, proto-Kinect, if you will. And we basically hung them in this kind of chandelier in the middle of the room. And the idea is you would turn it on, and it would transform the entire space into surface. Surface everywhere, right? So this is the 3D model that you get when you do a little bit of calibration of those cameras, bring them into the same world coordinate, same coordinate system. This part of the video, I'm just showing a couple of the little interactions that are fun, and then we'll go into each of these interactions a little more deeply. So the first one is all about thinking about multiple surface or multiple displays. How do we move things from one display to the next? Right? In the future, we're going to have displays everywhere, right? That's the idea. And how do we get data from one place to the next? Well, there's our surface kind of thing. We're doing this right now. That's just a piece of foam core. It's not a very special piece of hardware at all. And this is just a regular desk, the kind you get at Microsoft. And so you can sense when you're touching the desk and do these kinds of very surface manipulations, but then you'll notice that when he touches the one display and then touches the next, the object he's touching on the first one is transmitted almost as if like through his body to the other display. Here's another idea. You can then pick or pull the object into your hand. It turns into this red ball. It has a bit of physics behavior to it. You can drop it onto anything. Really, it doesn't need to be a piece of paper. It's just looking at the raw mesh data from the camera. And then you can pass it back, and it has a sort of physical tangible quality to it. Of course, there's nothing there. It's just light. So you don't really feel it there, but and you can pass it back and forth and do these kinds of manipulations. Here's another one. It's basically a menu. It's a very simple idea that you can maybe select items from a menu if you hold your hand over that spot on the floor and then pull up and raise your hand up and down to select an option. This is just one idea. Maybe we can do more things with widgets in space or projecting onto your body. Maybe the menu rolls out onto your arm when you touch an object. There's transmitting through two people, actually. It's showing that it's really, maybe you shake hands and the system detects that and you transfer information when you shake hands. This is a little bit of a view of how the system actually works. We have 3 depth cameras. This is, again, this is like the 3rd time I've shown these kinds of images already. In this case, the range is indicated by the pixel intensity. So the darker ones are closer, except for where it's black. So this is sort of a base level geometry. Here's my associate Horvath Benko is just walked in. I can recognize people pretty well just by their mesh at this point, at least people that I work with regularly. And so he's walking in, and here's a little close-up of that manipulation of that little ball that's rendered. You can see that things are a little bit noisy, but with appropriate amounts of smoothing, you can actually do some manipulation. There's what the menu looks like, similar kind of effect. And then this whole business of moving things from one display to the next is a little complicated, but what we're trying to do with the 3D cameras is actually emulate what surface would see if there were a surface unit there. Okay, so we're taking a projection of the 3D data and constructing an actual image that very roughly approximates what a camera would see if there were a camera under the table. And doing the same thing from the wall. And so you get this kind of effect. And so you can do all the kinds of surface processing or surface manipulations that we're familiar with, but on potentially any surface or any actual surface in the real world. This is a plan view of the space, and that can also be used to relate one surface to another. Basically, you connect from here to here through here, and through 3 different views. So that's a system I call Lightspace, and let's see, I think I'm probably running a little bit short on time. I want to squeeze one more in here just to loop back to Curtis's presentation a little bit, and also show a sort of completely different. I'm going to turn down this funky audio. So this is this is a system we've been playing around with. Now I showed you that pinching gesture, right? So imagine that you can actually pinch the graphics in this omnidirectional presentation, right? This is data right from a worldwide telescope, and we did a special version of Worldwide Telescope that allows you to project into a dome. This is something that was done with the principal developers of Worldwide Telescope. And then we basically, if you think about a multi-touch system, like your iPad or your Surface, what have you, when you touch, you get a contact, and it tracks that contact. If you get put down 2, you get 2 contacts. Well, here we're doing this pinch gesture. It's like we're doing multi-touch in space. Yeah, for every time you pinch, you actually create a contact. And there it is, right there. This is the camera. The camera actually is embedded with the projector. They share the same optical axis, in fact. It makes calibration very easy. The idea really of this system was that we wanted to build this thing. You wheel it into the room, you turn it on, and it transforms that entire room into an interactive surface, right? But of course, if you did that with one projector, with today's kinds of technology, today's projectors, it's not going to be bright enough. So we decided, hey, what we're going to do is we're going to put it in a dome. The first one we built was out of cardboard and latex paint and 2x4s. This one's a little more upscale. It's something you can blow up. It's like the bouncy toys that kids jump on at parties. And here's a view of when we take Roundtable, which is a 360-degree video teleconferencing product that came out of some work done at research, and actually put it in the dome. It's really interesting. Right now, there's all kinds of interesting sources of omnidirectional data, right? You have Worldwide Telescope, Roundtable, all the stuff the photosynth guys have done, you know, all the sort of gaming stuff can be ported directly into these kinds of environments. The idea that you could bring somebody into this environment and you know, interact with and point at various kinds of omnidirectional data, I think is quite real. Not every household will have one, I suppose, but yeah, and a few other things we've been playing around with. So I think that's all for now. I think I've probably overstayed my welcome. Any questions? Yes.
Yes. Thank you, Andy.
Yeah, I was. Show it to the microphone.
Go ahead. Just go ahead.
Just go ahead. I was wondering, with the way the surfaces are coming with the cameras, do you see any integration with this with some of the new feeling surface technology, like the Tesla Touch technology? Are you familiar with at Disney?
Yeah, I'm familiar with it. It's that is the sort of the big problem right now that everyone's having, is how to do those kinds of things and scale them up. Right? It's one thing to do the electrostatic thing you're talking about. It's something that's going to work on, you know, a device like this. Oh, by the way, you have to be moving in order to feel it. Right? So there's a bit of a limitation there. Some of the piezo stuff is another way of doing it. Doesn't work at the scale that we're talking about. It's the kind of thing that works on a handheld device. So
could maybe in the future, maybe like 10 years from now, maybe with that, when that touch technology for feeling surfaces progresses.
Yeah, I hope so. Well, that's one of the objections to the physics work that we've been doing, is like we've been doing some stuff where we're trying to emulate the physics of grasping behavior. Problem is there's nothing there. So nothing pushes back. And so that's the holy grail, I believe, of some of this haptic stuff, is to do that last little bit. Any more?
Question over here.
Just out of curiosity, given the fiasco with HP and their cameras having trouble detecting people of a darker skin color, is there any possibility that these installations, once released for further distribution, will include an IR camera so you can pick up heat as well as color and not have to worry about so much whether somebody is not a color bright enough to be picked up by the camera?
Almost all of the stuff that I showed you here is using infrared cameras. Okay. They don't actually sense heat, by the way.
Okay. But I'll be retarded for that. I don't.
It's the same frequency that your infrared remote control uses on your TV. So that doesn't get hot, right? But you can't see it. It's just beyond visible. And it just so happens that most materials in the natural world reflect infrared light. There are some exceptions. Asian folks' hair is an interesting one. No IR off of that. And that's actually a problem. But for the most part, it's not once you go to infrared. It's a good question. Thank you.
Maybe one more question for Andy?
Thank you for your presentation. I have done a little bit of experimenting with a Surface table, but somehow your presentation went well beyond my engagement. I'm going back to an earlier question I asked about an earlier presentation about big data, e-science, and collaboration over time and space by fast-forming teams. And you really got towards the data end at the end of your presentation. Now I'm trying to figure out, how does this scale up to the kinds of things where you really want to have the kind of blended worlds between virtual and physical, and use the analog ideas that you're dealing with as a way of building the human trust to form collaboration around big data and e-science?
Oh, wow. Yeah, I'm going to pass on the big data and e-science questions, but I will say that we have spent some time on a very large version of our tabletop system. I didn't show that, but it is something that we believe would be very useful for showing lots of information and getting 6 to 10 people around is something that we can do. Interestingly, one of the problems that we have is that the displays that we have do not have the resolution. Right? I have a 65-inch LCD panel in my lab. It's beautiful. It's still 1920 by 1080. Right? That'd be nice if it were one of the new 4K standards would come around. That's a real problem. I think, and the projectors are falling way behind on that curve. And so you'll notice that the Surface 2.0 product is more of like a 40-inch HD LCD.
So, I'm sure you've run across Ted Nelson's Xanadu from 30 years ago, probably before you were born. And a lot of what you're doing really, I recall that very, very clearly. In case I don't know, maybe you haven't.
You mean
made
the
that
resolution
connection.
problem? Or?
No, just the whole surface manipulation idea that you're working on.
Mm-hmm. Yeah,
it's very reminiscent of what was then a very futuristic idea.
Yeah, I mean, we owe a terrible debt to Myron Kruger and these guys, and in many ways what we're doing is just rediscovering and reinventing, and so I think one of the things that's different about it this time, of course, is that the fidelity of what we're doing is just very different. So, thank you.
Yeah, well, thank you very much, Andy, for joining us today. On a side note, at the I conference back at the Renaissance, we've got Microsoft will have a suite that'll be open tomorrow and Friday, and we're going to have a Surface there. Surface 1.0, Surface 2.0 are still kind of being manufactured right now, but it's a Surface 1.0, and I encourage you to drop by and play with it. We've got a few apps that came out with it and a few apps that our team in MSR has developed. So not quite as cool as the stuff that Andy was just showing you. That's kind of pushing the envelope, but we have a few things that I think will entertain you. Now I'd like to hand it over to Adnan Mahmud, who's from Microsoft Research Asia. He's actually based here in Redmond, but spends a lot of his time back and forth and represents a lot of the projects and a lot of the research that's happening in our lab in Beijing. And specifically, Adnan and myself, I've been working on something called Microsoft Academic Search, which some of you may have heard of, but if you haven't, I think you'll find it very, very interesting. So over to Adnan.
Can you guys hear me? I think you can, right? All right, good. All right, so we have looked at all those cool presentations, and you're wondering, man, I'd like to find out more about Andy Wilson, or you're wondering, I'd like to find out more about Microsoft Research because they're doing some really, really cool work. So how do you do that? How do you find scholars in different domains and find out the work they've done, papers they've written, people they've worked with, other researchers they've worked with? So in the interest of time, I am going to do a 5, maybe 3-minute version of the demo, and to show you what Lee referred to as the academic search. All right, so it is a beta service right now, and it is a public service. It's a long address. If you can remember, that's academic.research.microsoft.com. And right now, we only surface really this computer science data. We have about 8 million publications, papers, and 7 million authors. So clearly, we don't have 7 million authors in computer science. But we have other domains. But really, right now, the experience is focused only on computer science. So I'll walk through that. So let's start. And we'll start, let's say, with, let's say we start with Tony Hay. So type in Tony's name. So here is a profile about Tony, and it talks about some of the interests that he has. And I think Tony said earlier that he did a lot of work in particle physics before, which is not included here. It's almost, again, focused on computer science. So I can actually go through here and I can see all the publications that Tony was involved with. And then I can also see how many times they were cited. Let me go back to, okay, so Tony's part of Microsoft, so let me look at Microsoft here. And here are some of the computer science researchers in Microsoft. And you can see for each of them how many publications they have, how many citations they have. So I can, again, drill into one of these guys. And then here on the chart, you can see the number of publications, cumulative, and then number of citations, cumulative. Probably a better view might be the annual view. And you can see number of papers he has published per year and how often they were cited. Another interesting view here is the co-author graph, which will show you all the people that Mr. Lampert has worked on. I can zoom out to show you the whole graph here. And I can actually dig into any of these relationships, right? So when I hover over any of these lines, I can see between Leslie and Robert Shostak, 6 papers, right? And I can click on that and, let me see, click on the 6, and here are the 6 papers that they've worked on together, right? And I can again use this Visual Explorer to look at any of these other people, navigate around. So if I click on the person's name, it'll go and recenter the graph for that person. So now let's look at the paper side. So here are the papers that this people have worked on. And let's see one of these papers. So here is the paper, number of times it was cited, abstract from the paper, where it was published, location for you to get the paper. We don't actually store the full text of the paper. We direct you off to the original source. And then here is some of the context where the citations were made, and then the list of references for this paper. Again, very, very rich information. I showed you the author information, and now I'm showing you the information about a specific paper. You can find keywords related to the paper, other related papers as well. Now, one of the fun things, so let me show you some of the fun things here. Let's go back to the organization view. So here, you can see the list of organizations by number of citations that papers published from the organization has received, right? So Stanford, again, computer science, Stanford is 1, MIT is 2, Berkeley is 3, and you can talk to Tony after whether he agrees with this ranking or not. Cambridge and Oxford are higher than Southampton.
You don't have engineering in your bed.
Right. So I can actually even dig deeper, right? So I can say, like, let me filter this list for, let's say, just Europe, right? So here's the list in Europe. Or I could say filter it for, like, South America, for example, and you can see list for South America, right? Let's go back to the all continents, and let's look at Stanford. So one of the things that we did was we built this visualization for domain trends. So basically what this is showing you is how has the research focus in Stanford changed since 1960, right? And this is only focused on Stanford. Now what we can do is I can go back to our homepage and I can look at all domains and look at that one as well. This is across all computer science, all organizations, right? There's some interesting things that this points out. You can see that programming languages has kind of decreased its share as time has gone on, right? Whereas data distributed and parallel computing has clearly gone up significantly in the last 5 decades. Now what's really interesting is that, again, if I go back to Stanford University, sorry. And if you want to do some comparisons of how does the trend look for some of the bigger organizations, right? So let's look at Stanford. Let's look at domain trend of Stanford. And let's do another one. Let's do MIT. Actually, I should have done this a little differently. There we go. So here, so let's compare Stanford and MIT side by side. So you can see like there are very similar trends that go across those two universities. Let's look at the one where they're today, and you can see how the focuses of the two organizations are very similar to each other in terms of where the publications are happening. So I think I'm going to stop it right there. Questions? Right there.
Question about the citation tools. One of the challenges we have in using them is that they include self-citations. Is there a way that you've got in your tool that we can pull out self-citations to analyze a scholar's impact?
So by that you mean like how often that author cites his own papers or within the organization?
No, how often when an author cites their own papers, it kind of mucks up the data when you're trying to understand impact.
So one of the things we're working on right now is an extensibility plan, and really that's going to be through APIs. So you'll be able to actually access a lot of this data through APIs and create your own rankings and create your own calculations. So we might not provide a lot of those things on the site itself because we don't think we can address all of the needs, but that one you will be able to do it through APIs, and you can make your own calculations.
We use these a lot for promotion and tenure cases, and that's the big common problem with using most of these tools is we have to manually strip out self-citations. So just throw that out at some
point. That's great. So I'll take that back to our team, and we'll make we'll throw that in our feedback.
I've got a question over there next.
So I've always been amused by the fact that the faculty have different views of these kinds of things depending if they're a candidate for promotion and tenure or serving on the promotion and tenure committee. University presidents, provosts, and deans have different views of these things depending on what the ranking results were for their unit. But what's really, I think, interesting, and there are a couple of companies like Academic Analytics and some others, are really building towards what-if tools. So when you're recruiting somebody, you mentally try to say, well, if you get this person and put him with this cluster of faculty, maybe good things will happen. So to be able to drag that person in based on publication history and actually drop it in and find out what are the unusual effects that person could have in your current research cluster is clearly a tool that about 3 different companies are heading towards. Do you have any interest in those areas?
I think our interest is to make sure that we provide some of the most commonly used tools through our site. And again, like we're just starting this out and we're still in beta, so our focus is to make sure that we provide the 90% of the scenarios, right? And then going back to the earlier point, then we have the APIs where for the other 10% that we might not be able to serve, you will be able to do those on your own and create those calculations or what-if analysis.
Thought there was another question there.
Yeah, just on those last 2 questions. What are the plans for expansion? You mentioned that currently you're focusing.
Right, that's a good question. So we definitely want to get to multiple domains, all domains, so outside of computer science, and we're working hard with publishers, repositories, and libraries to get more content into our pipeline. So we hope that in the next few months, if not earlier, we will be able to put in more domains into the system and not just computer science. Does that answer your question? Your question was about the domains, right?
About expansion in general. Do you have an idea of what type of services, but also domain falls into that?
So domain expansion, yes. So that's definitely in our plans. In terms of expansion like APIs, as I said, that's also in our plans, right? So those are the 2 places where we're really focused on.
Yeah, and as you see, I've got to get my H index up and my G index. And what this doesn't count is all the references I have to e-science for people who aren't computer scientists. So I'm seriously worried about this. No, to be serious, what we would like to do is to make this as open as possible with if we can do open APIs so you can build your own things. And so you can do, your own analysis. Are there things we should be doing that we're not doing? Then I'll try and beat on poor old Adnan and his team to see if we can do them. Right. So what we'd like to do is make this responsive and collaborative and to try and produce something that is genuinely useful. perhaps even for 10-year decisions, who knows, but something that is actually of value to you guys. So please send suggestions to Lee, me, or Adnan.
Right, absolutely. And and I'm sure we'll share the contact info, but we'll also have the contact info on the website itself. So we always like suggestions. A bunch of our features come from suggestions from the community as well. So if you have ideas once you've tried it out, definitely send it to us.
Well, thank you very much, Adnan. So
Thanks,
great
Lee.
work.